Okay, let's take a short look at what conservation of momentum is. Let's do a little quick review first. And kinetic energy is a property an object has when it's moving. It's how much energy an object has. Now, when an object is moving and it has kinetic energy, some of this kinetic energy can be transferred to other forms of energy. We know this. It can be transferred to potential energy or even friction, or it can be transferred to some type of mechanical, other forms of kinetic or mechanical energy to do work. Momentum is another property that an object has when it's moving. And like kinetic energy, momentum is also a transferable property, and that's what we're going to take a look at for the next few minutes. Momentum is transferred when objects interact. Now, so what's an interaction? There's two types of interactions. There's collisions when particles hit each other, and there's explosions. An explosion might be one particle splits up into many particles. Now, on another level, it doesn't matter which type of interaction, whether it's a collision or explosion, momentum is still going to be transferred. And there's different types of collisions. There's an inelastic or elastic collision. I'm not going to look really too much at the difference today, but understand that momentum is transferred regardless of whether it's an inelastic or an elastic collision. Now, there is one little catch. There's one little condition that has to be met when momentum is conserved. Suppose you have a group of particles, and these particles are hitting each other. And when they hit each other, they apply a force to each other. If you add up all of the forces on all the particles involved in this interaction, and if this net force, if this total amount of force is 0, then we have what's called a closed system. Sometimes it's also called an isolated system. They mean the same thing. If we have an isolated system, that's what we're interested for. And if we have a closed system, we have conservation of momentum. Now, there's a mathematical proof for this. There's a mathematical proof that shows that with a closed system, when the net force is equal to 0, momentum is conserved. I'm going to skip it for now. I'm not going to get into those type of details. Just kind of maybe sometime in the future I might cover that. So just kind of bear with me for right now. Okay, what I just said earlier. In a closed system, net force of all the interacting particles is equal to 0. Momentum is conserved. That means the momentum goes unchanged from before the interactions to after the interactions. If you take the sum of all the momentums, which probably isn't the correct word, I think it's momenta, but if you take the sum of all the momentums of all the particles before the interaction, that is going to be equal to the sum of all the momentums of all the particles after the interaction. That's what the conservation of momentum means. All the momentum before the interaction equals all the momentum after the interaction. Now, momentum is just mass times velocity. And so mathematically, if we just look at two particles hitting, it looks something like this, where the mass of object 1 times its velocity plus the mass of object 2 times its velocity. Now right here, this part, mass 1, velocity 1, mass 2, velocity 2, is the total momentum before the interaction. On the other side of the equation, we have the same mass, mass 1, times its new velocity. That's what this little prime mark means. Whoops, sorry about that. Let's go back. So on the other side of the equation, we have this mass 1 times its velocity, but that's its new velocity. That's what this prime mark means. Plus mass 2 times its new velocity. So on this side of the equation, we have the new momentums of of the objects after they interact. This is the original momentums, the initial momentum before the interaction. This side is the momentums after they interact. And they're equal to each other. That's what conservation of momentum means. Now, depending on the type of interaction, kinetic energy may also be conserved. This is what's called an inelastic collision. I mentioned this a few slides ago. We have inelastic and elastic collisions. An inelastic collision, kinetic energy is not conserved. With an elastic collision, it is conserved. Not going to get into elastic collisions a whole lot. There's simply put, there's not that many elastic collisions in the world. Most collisions are inelastic, so that's what we tend to focus on. Keep in mind, momentum is a vector. So because of that, it is conserved. We have conservation of momentum in the x and y directions. So we can rewrite the previous equation that we have for conservation of momentum right here. We can rewrite it really for the x and y direction. Here's our conservation of momentum in the x direction. The mass of object 1 times the velocity of object 1 in the x direction plus the mass of object 2 times its velocity in the x direction before the interaction is equal to its mass of object 1 times its new velocity in the x direction plus the mass of object 2 times its new velocity. This is only in the x direction. And we do the same thing for the y direction. Momentum has to be conserved in all directions. And because momentum is a vector, the conservation of momentum applies in both the x and y directions.